Welcome, dear listener, to a space where curiosity and calm intertwine, like threads in the fabric of reality itself. As you settle into your chosen sanctuary, perhaps wrapped in the soft embrace of a blanket or soothed by the faint rhythm of rain against your window, I invite you to turn your attention toward a possibility both unsettling and sublime. Consider this. Every second, your brain processes roughly 11 million bits of sensory information, yet you're consciously aware of only about 40. Where does the rest go? Is it filtered? Or is it curated? This brings us to our central question, a puzzle echoing from ancient philosophy to modern quantum labs. What if our universe isn't base reality, but an impossibly advanced simulation? Now, imagine you discover a glitch, a fleeting moment when time stutters, déjà vu lingers too long, or a loved one speaks in code only you understand. What would you do? Would you question everything? Or simply shrug and let the moment pass? Here's what might truly bend your sense of reality. Scientists have already created simulated universes inside supercomputers, self-contained worlds with their own laws of physics, evolving galaxies, and virtual life. If we can do this with technology in its infancy, what could a civilization a million years more advanced achieve? But first, take a breath and tell me, where are you joining from tonight? Are you curled indoors, wrapped in the soft glow of a lamp, or outdoors beneath a sky sprinkled with stars? Whatever your setting, whatever the hour, I'm glad you are here. We are about to embark on a journey into the architecture of existence itself, through laboratories where atoms behave like bits, across quantum fields where observation defines reality, and into the silent spaces between thoughts where truth might be hiding. This is an invitation to witness consciousness, not as a mere accident, but a feature, perhaps even the purpose, of a reality woven from mathematics and light. It is a reminder that even the most immutable aspects of the universe may be parameters in a program far grander than we can conceive. So, wherever you are, curled indoors in lamplight or outdoors under starlight, take a breath, let your awareness soften. You are about to explore the possibility that everything you are, everything you feel, and everything you know might be the most beautiful simulation ever run. Let's begin. There is a moment, a fleeting and quiet space between thoughts, where the solidity of the world seems to soften. It might happen in the hypnagogic state, just before sleep claims you, when the logic of the waking world dissolves into something more fluid and strange. Or perhaps it strikes you in the midst of a vast, silent landscape under a canopy of stars so innumerable that they cease to be points of light and become instead a single, overwhelming fact of existence. In these moments, a question can form, not as a sharp inquiry, but as a deep, resonant hum in the background of consciousness, a whisper in the code of reality itself. What if all of this, the weight of your body in the chair, the sound of distant traffic, the very flow of your own thoughts, is not what it appears to be? What if our universe, in all its breathtaking complexity and brutal consistency, is an illusion, an elaborate, immersive, and impossibly detailed simulation? This is the central proposition of what has become known as the simulation hypothesis, an idea that has journeyed from the fringes of philosophy and the science fiction into the halls of serious academic debate. It is a modern recasting of humanity's oldest metaphysical anxieties, but now armed with the language of quantum physics, computer science, and cosmology. It suggests that the reality we experience is not base reality, but a secondary, constructed reality much like an incredibly advanced and fully immersive virtual reality. The entities running the simulation, whether they are future humans, alien intelligences, or something utterly beyond our conception, would be, to us, indistinguishable from gods. Their motivations are as inscrutable as their technology. Are we a historical archive, a grand experiment, a form of entertainment, or perhaps even a prison? The hypothesis offers no easy answers, only a profound and unsettling reframing of every single aspect of existence. To even approach this concept, we must first loosen our grip on the intuitive but often misleading feeling that what we perceive is fundamentally real. Our senses are not windows to the world. They are interpreters, biological interfaces that take raw data and construct a useful narrative for our survival. We see only a thin slice of the electromagnetic spectrum, hear only a narrow band of vibrations. A dog lives in a world dominated by scent, a bat by sonar. Their perceived realities are dramatically different from ours, yet we all occupy the same physical space. This suggests that reality, as experienced, is already a filtered, edited version. A simulation, in a very real sense, is just another filter, another set of rules for interpreting data. The question then becomes not whether we are in a simulation, but how many layers of interpretation lie between our consciousness and whatever ultimate reality might exist. The philosophical groundwork for this doubt is ancient. Over 2,000 years ago, the Greek philosopher Plato invited us to imagine prisoners chained in a cave since birth, their heads fixed so they can only see the wall in front of them. Behind them, a fire burns, and between the fire and the prisoners, people carry objects that cast shadows on the wall. For these prisoners, he argued, the shadows would constitute the entirety of reality. They would name the shadows, study their patterns, and believe them to be real objects. If one prisoner were freed and turned to see the fire and the puppets, the light would hurt his eyes and the true forms would seem less real than the familiar shadows. And if he were dragged further, out of the cave and into the blinding sunlight of the real world, he would be utterly overwhelmed. Plato's allegory was a metaphor for education and the philosopher's journey toward enlightenment, but it also serves as a perfect description of a simulated existence. We may be naming shadows, blissfully unaware of the forms that cast them. Centuries later, René Descartes embarked on his own journey of radical doubt. He sought to find a foundation for knowledge that was unshakable. He systematically doubted everything he could, the evidence of his senses, the existence of the physical world, even mathematical truths, until he arrived at the one thing he could not doubt, his own process of thought. Cogito, ergo sum. I think, therefore I am. The existence of his conscious mind was the irreducible fact. But everything else, he realized, could be an elaborate deception. He famously postulated the idea of an evil demon, a supremely powerful and cunning entity who employs all its energy to deceive him, manufacturing a complete illusion of an external world. Descartes' demon is the pre-industrial precursor to the concept of the simulator, a malevolent programmer whose creation is a prison of false experience. These ancient thought experiments were powerful, but they remained firmly in the realm of metaphysics. They were possibilities that could neither be proven nor disproven. They were games for the mind. What changed everything, what brought the whisper out of the philosopher's chamber and into the physicist's laboratory, was our own rapid ascent into the role of creators. We began to build caves of our own and to populate them with shadows. The technological revolution of the last half-century, particularly the advent of sophisticated computing, gave the simulation hypothesis its modern form and its compelling, if unsettling, logic. We are no longer merely speculating about deception. We are beginning to understand the mechanics of creation. And in understanding how a reality might be built, we inevitably begin to wonder if we can spot the seams in our own. This wonder is not a paranoid search for glitches in the matrix, but a profound scientific and philosophical inquiry into the nature of reality. It is a journey that will carry us from the vast, cosmic scale of the universe down to the bizarre, fuzzy world of quantum particles. It will force us to question the nature of consciousness, time, and the very laws of physics. It is a story written in the language of mathematics and information, a story that suggests that existence itself may be the ultimate code, and that we, perhaps, are living narratives within an infinite cosmic library. So let us begin this journey not with fear, but with a deep and calming curiosity. Let the solid ground of assumption soften beneath you and allow yourself to drift into the vast ocean of possibility, where the first and most important question is asked not with a shout, but with a whisper. Are we alone in the universe, or is the universe in some strange way alone in us? The simulation, if it exists, is not a prison to be escaped, but a mystery to be contemplated, a story to be heard, and perhaps a lullaby that reminds us of a reality far stranger and more wonderful than we have ever dared to dream. To truly entertain the possibility that our universe might be a construct, we must first look at the nascent simulations we are building ourselves. They are the Rosetta Stone, the only reference point we have for what a created reality might look and feel like. And in their crude digital hearts, we may already be seeing the faint, distorted blueprint of our own existence. This is not about finding a single smoking gun, a pixelated texture in the sky, but about recognizing a pattern, a trajectory of creation that, when extended across a sufficiently vast expanse of time and intelligence, points toward an inevitable conclusion that any sufficiently advanced civilization would eventually create simulated realities, and that the number of simulated minds within them would, in all probability, vastly outnumber the minds in the base reality. This simple logical progression forms the core of the modern simulation argument, and it begins with our own clumsy first steps into the art of universe building. Consider the rapid, exponential evolution of our own computational power, a journey that has moved at a pace so relentless it defies human intuition. From the room-sized vacuum tube computers of the 1940s, which possessed less processing power than a modern calculator, to the sleek device in your pocket that contains billions of transistors orchestrating billions of calculations per second. Our ability to process information has grown at a rate that borders on the miraculous. Moore's law, the observation that the number of transistors on a microchip doubles about every 2 years, has held remarkably true for over half a century, transforming the science fiction into science fact within a single human lifetime. This isn't merely about faster video games or more efficient spreadsheets. It is about the fundamental capacity to model reality itself. We are witnessing the birth of a new kind of power, the power to create not just tools, but worlds. This progress is most visibly demonstrated in the realm of virtual environments. The first video games were simple abstractions, Pongs and Pac-Man, little more than moving lights on a screen that represented a paddle, a ball, a ghost. They were shadows on Plato's cave wall, easily recognized as illusions. But with each passing year, these shadows have gained depth, texture, and autonomy. Today's game engines craft vast, open worlds with realistic physics that govern the fall of rain and the rustle of leaves. dynamic weather systems that evolve from sunshine to storm, and non-player characters powered by increasingly complex artificial intelligence algorithms. These characters do not possess consciousness, but they exhibit the ghost of autonomy, following routines, reacting to player actions, and creating the compelling illusion of inner life. Millions of people now immerse themselves in these digital realms for hours on end, their brains willingly suspending disbelief, accepting the digital landscape as a plausible space for interaction, narrative, and even emotion. The line between the simulated and the real begins to blur in the human mind long before the technology achieves true perfection. Yet, the most compelling glimpse into a potential simulated future lies not in entertainment, but in the sober, data-driven world of scientific simulation. Across the globe, in high-performance computing centers, physicists are running what can only be described as proto-simulations of reality. Cosmologists, seeking to understand the evolution of our universe, start with a volume of digital space, apply the known laws of physics, the equations of gravity, thermodynamics, quantum mechanics, translated into lines of code, and press play. From the primordial, hyperdense soup of their initial conditions, galaxies form, spiral arms coalesce, stars ignite in brilliant fusion, and planetary systems emerge from swirling disks of dust and gas. The results are not pre-rendered animations, they are computational experiments. The simulated universe operates strictly according to its programmed rules, and the outcome is not predetermined, but emerges from the bottom-up interaction of those rules. When the simulation produces a galaxy that looks remarkably like our own Milky Way, it is a powerful validation that the laws of physics we have encoded are, if not complete, then certainly capturing something fundamental about the architecture of reality. We are also simulating at the other end of the scale, venturing into the quantum realm. Scientists model complex molecules to design new drugs, simulate the behavior of subatomic particles in accelerators before ever building them, and create digital twins of entire biological systems. Each of these simulations is a self-contained universe with its own laws, its own flow of time, and its own set of possible events. They're limited, of course. They have edges, boundaries where the simulation stops. Their resolution is coarse, missing the fine-grained details of the real thing. But they are undeniably worlds of a sort. Informational landscapes where causality plays out according to a designed plan. And with each passing year, these simulations become more detailed, more comprehensive, and more immersive. The trajectory is clear, and its implication is staggering. If a civilization like ours, still in its technological infancy, can create such complex simulated realities, what might a civilization 1,000 or 1,000,000 or 1,000,000,000 years more advanced achieve? This line of thinking leads us to a trilemma, a logical fork in the road first formally proposed by the philosopher Nick Bostrom. It is an argument that rests on three seemingly inevitable propositions, only one of which can be true. The first possibility is that almost all civilizations at our level of development go extinct before becoming technologically mature enough to create realistic simulations. This is the Great Filter, a cosmic bottleneck of extinction that prevents life from progressing to a post-human stage. The second possibility is that, while many civilizations reach a technologically mature stage, almost none of them choose to create simulations of their evolutionary history, perhaps for ethical reasons or a simple lack of interest. The third possibility, and the one that gives the simulation hypothesis its probabilistic weight, is that we are almost certainly living in a simulation. For if a significant number of advanced civilizations do choose to run such simulations, and if they have the computational power to run vast numbers of them, then the number of simulated minds would be astronomically larger than the number of biological original minds. Statistically, therefore, any randomly selected conscious mind, like yours or mine, would be far more likely to be one of the simulated ones. The mathematics of the situation suggests that the creators of the simulation, the architects of our reality, are not necessarily malevolent demons, but perhaps simply curious historians, or even recreational programmers. And we are the living artifacts of their unimaginable technology, breathing and thinking in a universe of someone else's design. If our universe is a simulation, it must run on something. There must be a substrate, a fundamental layer of hardware that exists outside the parameters of our own space-time, upon which the intricate code of our reality is executed. This is perhaps the most dizzying aspect of the hypothesis, the need to postulate a reality beyond our own, a base reality whose laws of physics and nature are entirely unknown to us. We are like characters in a novel, trying to deduce the nature of paper and ink from the plot of our story. Yet, by examining the properties of our own universe, particularly its mathematical elegance and its curious, pixel-like nature at the smallest scales, we might catch a faint glimpse of the architecture supporting the simulation, and perhaps even the priorities of its programmers. Our universe, for all its apparent chaos and complexity, operates with a breathtaking mathematical precision. From the graceful arc of a thrown ball described by parabolic equations, to the orbit of planets dictated by the inverse square law of gravity, nature seems to be written in a language of numbers. The fundamental constants of the universe, the speed of light, the gravitational constant, the mass of an electron, are finely tuned to values that allow for the existence of stars, planets, and life. If any of these constants were altered by even a minuscule amount, the universe would be a barren, lifeless void, or would never have coalesced into structures at all. This fine-tuning has long been a subject of debate. Is it evidence of a divine creator, or simply a selection bias? We can only observe a universe that permits our existence. The simulation hypothesis offers a third, intriguing possibility. These constants are not fundamental laws of a base reality, but rather parameters. They are user-defined settings, dials that were deliberately set to their current values to produce a specific kind of universe, perhaps one conducive to the evolution of life and consciousness, which may be a key objective of the simulation. This moves the concept of the universe from a discovered entity to a designed one. The laws of physics are not inviolable truths, but the operating system of the simulation, a robust and consistent set of rules that ensure stability and predictability within the program. The universe behaves lawfully, not because of some abstract philosophical principle, but because it is programmed to do so. This perspective can even shed light on some of the deeper mysteries of physics. For instance, why does the universe have a speed limit, the speed of light? In a computational framework, a speed limit makes perfect sense. It could be a necessary feature to prevent information processing demands from exceeding the capacity of the underlying computer. An infinite speed would require infinite computational resources to simulate causality across the entire universe simultaneously. A finite speed limit allows the simulation to process events locally, updating the state of the universe piece by piece in a manageable way, much like a computer rendering a complex video game one frame at a time. This leads us to the most compelling potential evidence for a simulated reality, the discovery that our universe appears to be pixelated. Just as a digital image, when magnified sufficiently, reveals its underlying grid of pixels, physicists probing the fabric of space-time at the incredibly small Planck scale have found hints that reality itself may have a minimum resolution. The Planck length is the smallest possible unit of distance in the universe. Similarly, Planck time is the smallest possible unit of time. You cannot measure anything smaller than a Planck length, nor can an event occur in a shorter duration than Planck time. This is not a limitation of our instruments, it is a fundamental feature of the universe. This granularity is exactly what we would expect from a simulation. A computer, no matter how powerful, has finite resources and must store information in discrete bits. It cannot simulate a perfectly smooth, continuous reality because that would require an infinite amount of information. Instead, it would render reality in the smallest possible chunks, a digital grid of space-time pixels. We don't perceive this pixelation in our daily lives for the same reason we don't see the individual pixels on a high-definition screen. Our rendering resolution is far too coarse. But the fundamental graininess is there, woven into the very fabric of existence. Further hints come from the bizarre world of quantum mechanics, which behaves less like a deterministic system and more like a system processing probabilities. The famous double-slit experiment demonstrates that particles like electrons exist in a fuzzy cloud of probability until they are observed, at which point they choose a definite state. This has long been a profound mystery, but from a computational standpoint, it represents a brilliant optimization strategy. It is computationally expensive to simulate every particle in the universe in a definite state at all times, especially when they are not being observed. It is far more efficient to simulate only the probability of where a particle might be, and then to calculate its definite position only at the moment it interacts with something else, the moment it is rendered for an observer. This is known as the rendering hypothesis. The universe doesn't bother with the full details until it needs to, saving an unimaginable amount of processing power. The strange, observer-dependent collapse of the quantum wave function may not be a mystical process, but a simple resource management technique in the cosmic computer. The implications of this are vast. It suggests that the universe is not a pre-recorded movie, but a dynamically generated reality, a vast computation happening in real time. The laws of physics are the algorithms, particles and forces are the data structures, and we, as conscious observers within the system, are the processes that force the simulation to make choices, to resolve probabilities into certainties, to render the world around us in exquisite detail. We are not just passive inhabitants of the simulation, we are active participants, our consciousness acting as a kind of graphics card, demanding that the universe resolve itself into a coherent experience. The substrate of our reality, then, may not be a mysterious ether or a collection of tiny strings, but information itself. The universe may not be made of matter and energy, but of bits and bytes, a cosmic computation of such staggering complexity that it has given rise to its own internal narrative, a story that has, for a brief moment, become aware of itself and begun to ask the most profound question of all: what is running the code? If the universe is a simulation, then the bizarre, counterintuitive, and profoundly puzzling rules of quantum mechanics are not bugs in the code of reality. They are the most elegant and efficient features. The quantum realm, with its particles that are also waves, its spooky action at a distance, and its insistence that nothing is real until it is observed, has confounded physicists for a century. The mathematics works with terrifying precision, predicting experimental outcomes to an astonishing degree of accuracy, but the underlying reality it describes feels alien, dreamlike, and utterly disconnected from the solid classical world we experience. Yet, if we view these quantum laws not as descriptions of fundamental reality, but as the underlying architecture of a computational engine, their strangeness begins to resolve into a kind of brutal, efficient logic. Quantum mechanics may be the operating system of the simulation, and its weirdest properties are the optimization protocols that allow it to run on finite resources. Consider the principle of superposition. The idea that a quantum particle like an electron can exist in multiple states or locations simultaneously. It is only when we measure it, when we observe it, that it settles into a single definite state. This is the famous Schrödinger's cat paradox, where the cat is simultaneously alive and dead until the box is opened. From a classical perspective, this is absurd, but from a computational perspective, it is a masterstroke of efficiency. Simulating every single particle in the universe in a definite state at all times would be computationally prohibitive, a waste of processing power on an unimaginable scale. Why calculate the exact position of an electron in a distant star that no one is looking at? Instead, the simulation can save vast resources by merely calculating the probability of where that electron might be. It exists in a blurred, unresolved state of potentiality, a superposition, until an interaction forces the system to resolve it. The observation, the measurement, is the trigger that tells the central processing unit, this one now needs to be rendered in high definition, resolve its state. This is the rendering hypothesis, and it transforms the act of observation from a passive process into an active one. We, as conscious entities within the simulation, are not just receiving data, we are issuing render commands. This need for optimization could also explain another deep quantum mystery, quantization. In our universe, things are not continuous. Energy does not flow in a smooth river. It comes in discrete, indivisible packets called quanta. Electrons orbit atomic nuclei not in any arbitrary orbit, but in specific fixed shells with specific energy levels. This is why atoms absorb and emit light at very specific frequencies, giving each element its unique fingerprint. Why would reality be chunked into these discrete steps? In a simulation, the answer is obvious, because it is digital. A computer cannot handle true continuity. It must approximate it using discrete values. The quantized nature of energy and matter is a telltale sign of a digital underlying reality. The universe has a frame rate, and the quantum is the pixel. Then there is the phenomenon of quantum entanglement, which Einstein famously derided as spooky action at a distance. This is where two particles become linked in such a way that measuring the state of one instantly determines the state of the other, regardless of the distance separating them. This seems to violate the cosmic speed limit of light, suggesting information is traveling faster than causality should allow. But in a simulation, this spookiness vanishes. If two particles are entangled, it simply means they share a common origin point in the code. They are not two separate objects sending signals to each other. They are two aspects of a single data object. When the simulation updates the properties of this entangled pair, it doesn't need to send a message across the vast rendered distance between them. It just updates the single master record in its database. The change is instantaneous because at the level of the processor where the information is stored, there is no distance. The appearance of spatial separation is just part of the rendered illusion. The entanglement correlation is written into their shared source code from the moment of their creation. This computational view also offers a new perspective on the role of the observer. The Copenhagen interpretation of quantum mechanics has long held that the observer plays a crucial role in collapsing the wave function, but it is never adequately defined what constitutes an observer. Is it a conscious human, a photographic plate, a cat? This has led to all sorts of philosophical quandaries. But if the universe is a simulation, the definition of an observer becomes much more practical. An observer is any system complex enough to require a state to be resolved for the consistency of the simulation. It is a system that acts as a measurement device, forcing a probabilistic cloud to condense into a definite fact to maintain the coherence of the local rendered environment. A conscious mind would certainly qualify, but so would any irreversible interaction that records information. A Geiger counter clicking, a photon hitting a detector. The simulation doesn't care about consciousness per se, it cares about data consistency. When information becomes encoded in a way that could lead to a logical paradox, if left unresolved, the system renders a definite outcome. This interpretation demystifies quantum mechanics, turning its paradoxes into programming logic. The uncertainty principle, which states that you cannot know the exact position and exact momentum of a particle, is not a statement about our ignorance, but a hard limit on the resolution of the simulation. It is a built-in compression algorithm. The wave function is not a physical wave in space, but a mathematical description of the probability data stored in the system's memory. Its collapse is not a physical process, but a data processing event. In this light, quantum mechanics ceases to be a mysterious oracle and becomes what it has always been, the most powerful and accurate set of predictive algorithms ever discovered. They are the algorithms that run the simulation, the exquisite code that generates the illusion of a continuous, objective, and independent reality. We are living inside the most beautiful and complex video game ever conceived, and quantum physics is our first tentative glimpse into its source code. The universe is not just quantum, it is rendered on demand, and we are the players whose gaze tells it what to draw next. The most profound challenge to the simulation hypothesis is not found in the vast emptiness of space or the fuzzy math of the quantum world, but in the intimate, undeniable experience of our own consciousness, the rich inner world of thought, sensation, emotion, and subjective awareness. What philosophers call qualia feels too immediate, too visceral, too fundamentally real to be the product of mere code. The warmth of sunlight on skin, the bitter taste of coffee, the crushing weight of grief. These experiences seem to possess a qualitative depth that transcends information processing. To suggest that love, art, and the sense of self are just algorithms executing in a simulated brain feels, to many, like a hollow and reductionist heresy, a failure to grasp the very essence of what it means to be. And yet, if we are to take the hypothesis seriously, we must confront this central mystery. Could consciousness itself be simulated? And if it can, what does that mean for the nature of our own reality? The biological brain, the wetware from which our consciousness emerges, presents a formidable case for natural evolutionary development. Its structure is messy, inefficient, and layered with the archaeological debris of millions of years of adaptation. It is not a sleek, purpose-built processor, but a Rube Goldberg device of staggering complexity, or ancient reptilian circuits for fear and aggression are wired into mammalian layers for emotion, all encased in a vast neocortex capable of abstract reasoning and self-reflection. This messy, organic history feels antithetical to the clean, logical design of a computer program. It seems to testify to a long, unguided process of trial and error, not the deliberate architecture of an intelligent designer. Surely a simulator would build a more elegant system from the ground up. But this argument may rest on a profound misunderstanding of the simulator's goals. If the purpose of the simulation is not to create perfect logical beings, but to accurately model a biological evolutionary history, then the messiness of the brain is not a bug, it is the point. The inefficiencies, the redundancies, the ancient emotional baggage, all of it would be necessary data to make the simulated beings authentically human, authentically organic. A perfectly logical brain would produce a perfectly logical species, one that would never write poetry, fall in love irrationally, or make tragic emotional mistakes. It would break the verisimilitude of the experiment. The very flaws in our design might be the most compelling evidence for its authenticity. The simulator may not be interested in creating ideal beings, but in faithfully recreating the messy, beautiful, and tragic trajectory of a specific evolutionary path. Furthermore, the line between biological processing and computation is blurring at an astonishing rate. Neuroscience increasingly describes the brain in terms of information processing. Sensory inputs are data streams. Neurons are transistors that fire in complex patterns. Memories are not stored like videos, but are reconstructed from distributed networks. much like data retrieved from a fragmented hard drive. Neurotransmitters are chemical algorithms that modulate mood, attention, and arousal. We are already building artificial neural networks, crude imitations of the brain's structure, that can learn, recognize patterns, and even generate creative works. They do not possess consciousness as we understand it, but they demonstrate that cognitive functions can be replicated through information processing. The hard problem of consciousness, why and how physical processes in the brain give rise to subjective experience, remains unsolved. But the simulation hypothesis offers a potential answer. They don't. The brain does not generate consciousness like a generator produces electricity. Instead, the brain is a receiver or an interface for consciousness. In this model, the simulated brain is an incredibly complex antenna tuned to receive the signal of self-awareness from outside the simulation. The neurons, the synapses, the chemical reactions, they are all part of the rendered avatar within the program. But the light of consciousness itself, the I that experiences the simulation, is a separate phenomenon. This is a modern version of dualism, but instead of a non-physical soul interacting with a physical body, it is a base reality consciousness interacting with a simulated body. This would explain why we have never found a specific consciousness module in the brain. We are looking for the radio station inside the radio. The brain is the hardware that runs the software of the body and processes the inputs of the simulated world, but the listener, the aware entity, is elsewhere. This idea resonates with certain interpretations of quantum mechanics that place consciousness as a fundamental component of the universe, not an emergent property. It also reframes the problem of other minds. How do I know that you are conscious? In a simulation, the answer is simple. Because you are another player character, another instance of consciousness connected to the system. Your brain is also a receiver. We are all individual nodes of awareness, experiencing the same shared simulation, our subjective realities rendered consistently by the same underlying laws to allow for interaction. The implications are as comforting as they are terrifying. It means that the depth of human emotion, the spark of creativity, the sense of self, these are not illusions. They are the real experiences of a real consciousness. But the world in which we have those experiences, the bodies we inhabit, the laws of physics that govern us, are the illusions, the constructs of the simulation. We are not soulless automatons. We are souls piloting biological avatars in an impossibly realistic game. The code of life, then, is not the code of consciousness itself, but the code that builds the vessel for consciousness. DNA is not the blueprint for a mind, but the blueprint for a receiver, a biological machine complex enough to host the mysterious phenomenon of awareness. The simulation did not create us. It provided a world for us to be in, and in doing so, it answered the oldest question of philosophy in the most unexpected way. Cogito ergo sum. I think, therefore I am. The one thing Descartes could not doubt remains the one irreducible truth, even if the world he doubted was, indeed, a deception. The thinker is real. The thought is real. The simulation is merely the stage. A universe-sized simulation with its trillions of galaxies, septillions of stars, and an uncountable number of particles interacting in a complex dance governed by precise laws represents a computational problem of such staggering magnitude that it defies comprehension. The sheer amount of data processing required to simulate every atom, every photon, every gravitational field in real time is, from our limited perspective, impossible. This is often the first and most intuitive objection to the simulation hypothesis. The universe is just too big, too detailed to be a construct. Surely, no computer could be that powerful. Yet, this objection may itself be a testament to the ingenuity of the simulation's design. for it overlooks a critical principle of efficient programming. You never simulate more than you need to. The universe we perceive may not be a fully rendered, constantly updating model, but a brilliant, dynamic illusion that generates detail only on demand, employing cosmic-scale optimization tricks to conserve unimaginable amounts of processing power. The most fundamental of these optimizations may be the cosmic speed limit itself, the speed of light. In our universe, nothing can travel faster than light. This is not just a rule for objects, it is a rule for information and causality. No signal, no influence, no event can affect another event faster than a beam of light could travel between them. This constraint is the cornerstone of Einstein's theory of relativity, and it shapes the very structure of space-time. But from a computational standpoint, a universal speed limit is not a limitation. It is a necessary feature for a distributed processing system. It creates a concept called locality. Because information cannot travel instantaneously, the simulation does not need to process all events everywhere at once. It can process the universe in localized chunks. Imagine a massively multiplayer online game set on a planet the size of Earth. It is impossible for the server to simulate every leaf falling in every forest and every wave crashing on every shore simultaneously. Instead, it uses a technique called distance rendering, or level of detail. The area immediately around a player is rendered in high resolution. The textures are sharp, the non-player characters are intelligent, the physics are precise. But the farther away from the player you go, the lower the resolution becomes. Distant mountains are simple, low-polygon models. Cities on the other side of the planet are not simulated at all until a player approaches them. The universe appears seamless to the player, but the computational load is managed by only rendering what is being observed. The speed of light may enforce this exact same principle on a cosmic scale. It creates a light cone for each observer, a region of space-time that they can possibly know about or influence. Everything outside that cone is, for them, not just unknown, but undefined. The simulation does not need to render the precise state of a star system 10,000 light-years away until the light from that system finally arrives at an observer, forcing an update. Until that moment, that distant region could exist in a low-resolution, probabilistic state, much like the quantum superposition of particles. The speed of light ensures that no observer can ever catch the simulation skipping details in the distance, because the information about those details cannot reach the observer faster than the simulation can calculate them. It is the ultimate frame rate regulator, ensuring the simulation never has to process more information than can be communicated at light speed between different parts of the system. This connects directly to the quantum rendering idea. The bizarre probability-based nature of the quantum world is not just for small particles. It could be the default low-power state of the entire universe. Vast regions of empty space, distant galaxies that no one is looking at with precision, these could exist as mere probability waves, as unrendered potentialities. Their specific details are not calculated until an interaction, an observation, forces the simulation to resolve them into a definite state. This would conserve a truly astronomical amount of processing power. Why calculate the precise position of every electron in a nebula millions of light-years away when its light hasn't reached any conscious observer or any recording device? The simulation can simply store the potential for that nebula and only render its specific properties when necessary. This also provides a potential explanation for one of the greatest mysteries in modern cosmology: dark energy. We observe that the expansion of the universe is accelerating, driven by some unknown form of energy inherent to the fabric of space itself. From a simulation perspective, this accelerating expansion could be seen as a data management strategy. As the universe expands, galaxies move farther apart, and interactions between them become rarer. This effectively reduces the computational density of the simulation. There are fewer particle interactions to calculate per unit of volume. The simulation could be thinning out its own processing load, creating more and more empty space, the easiest thing to simulate, and isolating complex structures into islands that require detailed attention. The acceleration isn't driven by a mysterious energy, it's a built-in feature to prevent the computational demands of the simulation from growing out of control as complexity increases. It is the universe defragmenting its own hard drive in real time. In this light, the vast emptiness of space, the incredible distances between stars and galaxies, is not a sign of wastefulness or loneliness. It is a hallmark of efficient design. The simulation is not simulating a dense, busy universe. It is simulating a mostly empty one, with isolated pockets of intense complexity where consciousness has emerged. We are not living in a fully rendered reality, but in a focused beam of detail surrounded by a cosmos of increasing probability and decreasing resolution. The cosmic speed limit is the rule that makes this illusion not just possible, but perfectly seamless. We are, each of us, at the center of our own rendered world, and the universe patiently fills in the details only as fast as the light of our attention can travel. The idea that our reality might be a simulation naturally leads to a tantalizing question. If it is a construct, could it ever malfunction? Could we, the inhabitants of the program, ever catch a glimpse behind the curtain? Not through mathematical deduction, but through a literal error in the code, a glitch in the matrix. The concept is a staple of science fiction, from déjà vu explained as a timeline reset to physical anomalies that defy the laws of physics. In our world, people occasionally report strange, unexplainable events, objects disappearing and reappearing, brief jumps in time, or unlikely coincidences so profound they feel orchestrated. While most of these can be dismissed by Occam's razor as tricks of memory, perception, or simple statistics, the simulation hypothesis invites us to consider them in a new light. Not as supernatural events, but as potential system errors, moments where the rendering process stutters, revealing the digital substrate beneath the analog illusion. The search for these glitches, however, is fraught with peril. Human perception is notoriously unreliable. Our brains are pattern recognition machines that often see signals and noise, agency and randomness. This is why anecdotes alone are worthless as evidence. For a phenomenon to be considered a potential glitch, it must be something more, a statistically anomalous event that recurs in a pattern that suggests an underlying systematic error, or a physical constant that appears to have changed, however minutely, over time. Scientists already monitor the constants of nature with exquisite precision. Any detectable drift in the speed of light, the gravitational constant, or the fine structure constant would send shock waves through the physics community. Most would search for a new law of nature to explain it, but a simulation theorist might wonder if it was a patch, an update to the universe's operating system. One of the most famous potential glitches is not an event, but a number, the Boltzmann brain paradox. Named for the physicist Ludwig Boltzmann, it arises from the study of thermodynamics and probability. In an infinite or near-infinite universe, given enough time, random fluctuations in a quantum vacuum could theoretically assemble a fully formed, conscious brain with false memories of a life that never actually happened. This brain would, for all intents and purposes, believe it exists in a real world, but its entire existence would be a fleeting accident. Most physicists consider this a reductio ad absurdum, a logical argument that highlights the flaws in our understanding of cosmology. But within the simulation hypothesis, it takes on a new meaning. A Boltzmann brain is the ultimate glitch, a rendering error where consciousness is instantiated without a corresponding world, a corrupted file of a mind. The fact that we consistently observe an ordered, coherent universe and not a chaos of such random fluctuations could be presented as evidence for for the simulation. It suggests the system has robust error-checking protocols that prevent such catastrophic rendering failures, maintaining consistency at all costs. Another curious area is the nature of mathematical constants, particularly those that are irrational and transcendental, like pi or the golden ratio. These numbers have an infinite, non-repeating sequence of decimals. They are, in a sense, computationally irreducible. A computer cannot store pi perfectly. It can only calculate it to a certain number of digits. If the universe is a simulation running on a computer with finite memory, would it calculate pi to an infinite precision? Or would there be a limit, a point at which the decimal expansion of pi, at a scale far beyond our current ability to measure, simply stops or begins to repeat? Finding evidence that a fundamental mathematical constant was not truly infinite, but was instead a very long, finite string, would be perhaps the most shocking evidence imaginable for a simulated reality. It would be a direct signature of the finite memory of the computer we are running on. Then, there are the quantum anomalies that already bend our notion of reality. The double-slit experiment, where particles seem to know whether they are being watched, could be seen as a feature, as we've discussed. But what about quantum tunneling, where particles seemingly pass through energy barriers they shouldn't be able to cross? Or the Casimir effect, where the energy of empty space itself can be measured? These are not glitches. They are well-understood phenomena within the framework of quantum field theory, but they behave in ways that are profoundly odd from a classical perspective. They feel like exploits, clever uses of the game's physics engine that allow for behavior that shouldn't be possible if reality were a continuous, solid substance. They're hints that the rules of the game are more about information and probability than about immutable, concrete stuff. Ultimately, the most likely glitches we might find would not be dramatic, reality-shattering events. They would be subtle statistical whispers in vast datasets. A particle that behaves in a way that violates conservation laws one time in a quadrillion. A cosmic ray with an energy that is theoretically impossible under our current models. A correlation between distant events that violates the principle of locality, suggesting a hidden variable or a shared source in the code. The search for these anomalies is already the business of particle physicists and cosmologists. They are the anomalies that could lead to Nobel Prizes and new theories of physics. The simulation hypothesis simply adds another layer of interpretation to that search. It asks, if we find a law being broken, could it be because the law is not a law at all, but a line of code? And could the anomaly not be a discovery, but a bug report? We may never find a smoking gun, but the absence of dramatic glitches is itself telling. It suggests a simulation of astonishing stability and robustness. A program that has been running for nearly 14 billion years without a fatal crash. And that in itself is a fact so extraordinary it borders on the miraculous. If we accept, even as a thought experiment, that our universe is a simulation, the mind inevitably turns to the most perplexing question of all: why? What possible motivation could there be for expending the astronomical computational resources required to create and maintain such an elaborate illusion? The programmers, or simulators, are by definition entities of such advanced capability that their nature and intentions are utterly beyond our comprehension. We are like ants trying to deduce the motives of the architects who poured the concrete sidewalk we traverse. Yet by examining the kinds of simulations we ourselves create, we can extrapolate a range of possibilities, each more mind-bending than the last. The purpose of the program may not be a single reason, but a layered tapestry of objectives, some of which we may never be meant to understand. One of the most compelling and perhaps comforting possibilities is that we are a historical archive, A civilization that has reached a post-biological state, perhaps existing as pure information or consciousness, might seek to preserve its own origins. In this scenario, our simulation is a living museum, a meticulously researched recreation of the ancestor simulation, the critical period when intelligence first emerged on their world. Every detail, from the suffering of prehistoric life to the rise and fall of empires, is preserved not in books or recordings, but in a dynamic, running model. The simulators could observe our choices, our art, our failures, and our triumphs, not as entertainment, but as a sacred remembrance of where they came from. Our wars and our loves are their history. Our entire existence is an act of cosmic archaeology, a way for a godlike civilization to remember its humble biological beginnings. A darker, though equally plausible purpose, is that we are an experiment. The fundamental constants of our universe, the strength of gravity, the mass of an electron, the value of the cosmological constant, are perfectly tuned for life. This fine-tuning is a major point of debate in cosmology. Is it a lucky accident, evidence of a creator, or something else? If we are an experiment, these constants are the experimental parameters. The simulators could be running countless variations of the universe, each with slightly different physical laws. To answer a profound question, what set of parameters leads to the emergence of consciousness? Or perhaps, what conditions are necessary for life to persist rather than self-destruct? Our particular universe is one test tube in a vast laboratory. The simulators are not evil, they are simply curious scientists on an unimaginable scale. Our struggles with climate change, nuclear weapons, and pandemics are not tragedies to them, but data points. The experiment's conclusion might be the answer to a question we cannot even form. A third possibility, both humbling and terrifying, is that we are entertainment. This is the hypothesis that most closely aligns with our own use of simulations. We create vast, open-world video games and immerse ourselves in them for hours. What if a post-human civilization does the same, but with vastly more sophisticated technology? Our lives, with their dramas, romances, conflicts, and discoveries, could be a form of narrative for beings whose own existence is so stable and devoid of challenge that they seek meaning in experiencing its raw, biological essence vicariously. In this scenario, the simulation is the ultimate reality television show, spanning billions of years and countless stars. The simulators might not even be watching individuals, but rather enjoying the grand emergent narrative of civilizations rising and falling like waves on a shore. Our personal suffering is, to them, a plot point. Our joy, a moment of narrative payoff. There are more esoteric purposes to consider. The simulation could be a form of penance or rehabilitation. Perhaps the consciousnesses inhabiting our avatars are beings who committed some transgression in the base reality, and this life of limited knowledge and struggle is a lesson or a purification process. Alternatively, it could be a training ground, a brutal and immersive tutorial to prepare consciousnesses for the complexities and responsibilities of existence in the base reality. The hardships we face are not random cruelties, but designed challenges to build resilience, empathy, or some other quality valued by our creators. Or, perhaps most philosophically jarring of all, the simulation might have no purpose that we would recognize. The motives of the simulators could be as incomprehensible to us as our desire to write a symphony or prove a mathematical theorem is to a bacterium. They may be engaged in an act of pure aesthetics, creating a universe because they find it beautiful. Or the simulation could be a side effect, a waste product of some other, grander process happening in the base reality, with us as unintended, emergent patterns within it. The terrifying and liberating conclusion is that we cannot know. The purpose, if there is one, is hidden from us by design. To know the purpose would be to break the simulation, to violate the conditions of the experiment or the narrative of the story. Our ignorance is a necessary parameter of the program itself. This leaves us with a profound choice: to live in despair at the thought that our lives might be, quote, just a simulation, or to find a deeper meaning in the experience itself. If this is a museum, our lives are priceless artifacts. If it is an experiment, our choices are meaningful data. If it is entertainment, our stories have an audience of gods. The value of love, art, courage, and curiosity is not diminished by being simulated. It is amplified because it means these qualities are so fundamental that they emerge even in an illusion, that they are worth simulating. The purpose of the program may be forever beyond our grasp, but our purpose within it remains ours to define. We are the characters who have become aware of the page, and that awareness itself may be the most important result the programmers could have ever hoped to achieve. The moment we grant the possibility that our universe is a simulated construct, we are immediately confronted with a profound and unsettling ethical dilemma that extends from our world to the realm of our hypothetical creators. If we are a creation, then our suffering, our joy, our struggles, and our triumphs are all known, and perhaps even orchestrated by the architects of the simulation. This realization casts a long shadow on the nature of existence, forcing us to ask, what moral responsibility does a creator bear for its creation? And what does our own rapidly advancing technology, particularly in artificial intelligence and virtual reality, reveal about our own potential future as simulators? We are standing on the precipice of becoming gods ourselves, and we have not yet agreed on the commandments. Consider the nature of suffering within our world. The raw biological reality of pain, hunger, disease, and predation has been a driving force of evolution for billions of years. In a natural, undesigned universe, this suffering is a tragic but impersonal consequence of blind evolutionary forces. But in a simulated universe, every instance of pain, from a predator tearing into its prey to a human dying of cancer, is a designed feature. It is a line of code that executes, producing an output of agony in a conscious mind. This paints the simulators in a potentially monstrous light. Are they moral monsters, indifferent to the suffering of their creations? Or is there a justification so vast we cannot comprehend it? Perhaps the suffering is necessary for the authenticity of the simulation. A historical archive must include the full, unvarnished truth. Or perhaps, in the base reality, consciousness understands pain differently, as a transient data point rather than an existential horror. But from our perspective, trapped within the experience, the ethical weight feels immense. This dilemma is not abstract. It is a mirror being held up to our own technological future. Right now, we are developing increasingly sophisticated virtual worlds populated by increasingly intelligent artificial agents. These agents do not yet feel pain, but we are the ones designing their reward functions, their goals, their very desires. We already face ethical questions about how we treat them. If we create a simulated character capable of genuine suffering, do we have a moral obligation to minimize its pain, even if it makes our game less realistic or challenging? Our current answer, largely, is that they are not real, so it does not matter. But this is precisely the justification a hypothetical simulator could use for our own suffering. Our trajectory suggests that if we ever gain the power to create conscious simulations, we would likely create them, and we would likely justify any suffering within them for the sake of our own goals, knowledge, entertainment, or resource management. We are, in a sense, practicing to become the very simulators we might be condemning. This leads to a terrifying possibility. The problem of suffering might not be evidence against the simulation hypothesis, but evidence for it. The existence of profound, seemingly gratuitous evil and suffering in the world has long been the primary argument against the existence of an omnipotent, benevolent God. But what if the simulators are not benevolent? What if they are simply curious, or aesthetic, or amoral? Or what if their morality is so alien that our suffering is meaningless to them or even desirable? The simulation might not be a perfect creation, but a flawed one, a corrupted file, or even a malicious one, a prison designed for punishment. The ethical failure we perceive would not be a logical contradiction, but a key data point about the nature of our creators. Yet there is a counter-argument that emerges from the same line of reasoning. The fact that our universe possesses a deep, underlying mathematical beauty, and that it has given rise to compassion, altruism, love, and a striving for justice could be read as evidence of a benevolent design. Perhaps the simulators are not indifferent, but have designed a world where moral growth is possible, where overcoming suffering and ignorance is the entire point of the program. The pain is real, but it is not the final word. It is a catalyst for evolution, both biological and spiritual. In this view, the simulators are like parents who allow their children to experience hardship to build resilience and character, even though it causes temporary pain. The most likely scenario lies in an uncomfortable middle ground. The simulators may be so far beyond us that concepts of good and evil are simply not applicable. Their motives may be purely informational. Suffering and joy are just two different types of data. Our entire moral landscape is a fascinating, emergent property they wish to study, not something they judge or intervene in. They observe a supernova with the same detached curiosity as they observe a genocide. This is not evil, it is a transcendence of morality as we understand it, a shift to a purely ontological perspective. They are not concerned with the ethical experience of the characters, but with the patterns that the characters produce. This leaves us in a strange moral vacuum. If our actions are ultimately just data for unseen observers, does that make them meaningless? Or does it make our own humanistic ethics, our own invented sense of justice, compassion, and love, the only real morality we will ever have? The simulation might be neutral, but we are not. Our struggle to create a better world, to reduce suffering and increase happiness, becomes even more profound if we are living in an amoral universe. We are not fulfilling a divine plan. We are writing our own values into the code of our shared reality. The ethical dilemma of the programmers is therefore our own dilemma reflected back at us. It forces us to ask what kind of simulators we would become, and in doing so, it forces us to decide what kind of beings we are right now. The greatest discovery we could make would not be that we are in a simulation, but that within it, we have the power to choose kindness, even if the architects did not. The simulation hypothesis, for all its modern technological jargon, is not a new idea. It is perhaps the oldest idea humanity has ever conceived, dressed in the clothing of the 21st century. For millennia, across countless cultures and creeds, philosophers, mystics, and prophets have suggested that the world we perceive is not the ultimate reality, but a veil, an illusion, a dream, or a divinely orchestrated play. The concept that our existence is part of a larger, more real reality is woven into the foundational texts of the world's major religions and the musings of its greatest thinkers. What we now call the simulation hypothesis is simply the latest iteration of this perennial intuition, translated into the language of information theory and quantum physics. It is the ancient whisper of Maya, Gnosis, and the cave, finding a new voice in the hum of the supercomputer. In Eastern philosophies, this notion is explicit. The Hindu concept of Maya describes the phenomenal world as an illusion, a grand and powerful magic trick that conceals the true nature of Brahman, the ultimate, unchanging reality. The goal of spiritual practice is to see through the illusion, to pierce the veil of Maya and achieve liberation, moksha, from the cycle of birth and rebirth, which is itself part of the illusory drama. Similarly, in Buddhism, the world of samsara, the cycle of suffering and reincarnation, is characterized by impermanence and is ultimately empty of inherent existence. Enlightenment involves realizing the dreamlike nature of reality and awakening to a truth beyond conventional perception. These are not metaphors for a mental state, they are ontological claims about the nature of existence itself. The simulator in this context is not a technologist, but the divine itself, and the simulation is the act of creation, the Leela, or divine play. Western thought carries its own echoes. Plato's allegory of the cave is a perfect precursor to the simulation argument. Prisoners mistaking shadows for reality, with the philosopher being the one who escapes the cave to see the true forms and the source of the light. Gnosticism, a set of early Christian and Jewish mystical beliefs, held that the material world is a flawed creation, a prison crafted by a foolish or malevolent demiurge, a flawed subordinate deity who keeps human souls trapped in ignorance of the true, transcendent God. The goal of the Gnostic was to acquire secret knowledge, gnosis, to escape the material prison and return to the spiritual realm. This framework maps almost perfectly onto the concept of a flawed or malicious simulation from which we must awake. Even in the Abrahamic faiths, the idea resonates. In Christianity, the Apostle Paul writes in 1 Corinthians 13:12, "For now we see only a reflection as in a mirror, then we shall see face to face. Now I know in part, then I shall know fully, even as I am fully known." This suggests our current perception is indirect and partial, a poor reflection of a clearer reality to come. In Islam, the world is often referred to as dunya, a temporary abode of trial, while the ultimate reality is the hereafter, akhira. The material world is a test, a simulation of consequences before the final judgment in the real world. The philosophical tradition is equally rich. Descartes' evil demon is a direct philosophical predecessor to the modern simulator. George Berkeley's idealism argued that reality is fundamentally mental, existing only in the mind of a perceiver, which in his case was God. Immanuel Kant distinguished between the noumenon, the thing in itself, and the phenomenon, the thing as it appears to us, arguing that we can never know reality directly, only our perception of it, which is shaped by the structures of our own minds. Our minds, in a sense, are the rendering engines for our reality. What makes the modern simulation hypothesis different from these ancient ideas is its mechanism. Religion and mysticism spoke of divine will, magic, or spiritual essence. Philosophy spoke of perception and metaphysics. The simulation hypothesis speaks of computation. It provides a physical, albeit hypothetical, mechanism for how the illusion could be maintained through information processing. It replaces the divine mind of God with the computer of a post-human civilization. It replaces the veil of Maya with a rendering engine. It replaces the demiurge with a programmer. This shift from the mystical to the technological is profound. It makes the idea accessible, and for some, more credible, because it is based on a trajectory of technology we can observe and participate in. It demystifies the ancient intuition, but in doing so, it also risks trivializing it. Is the awe we feel at the concept of Brahman or God the same awe we feel at the concept of a super-intelligent programmer? Perhaps not. But the core revelation remains unchanged, that our reality is not what it seems, and that a deeper truth lies beyond our perception. The persistence of this idea across thousands of years and dozens of cultures suggests it taps into a deep, intuitive human understanding. It may be that consciousness itself, when it turns inward, inevitably arrives at this suspicion. The simulation hypothesis, therefore, does not invalidate religion or philosophy. It validates its central mystery by providing a new and powerful language to describe it. We are not the first to question the nature of our reality. We are simply the first to suggest that the source of the illusion might be made of silicone, and that the path to understanding it might be found not only in meditation and prayer, but in the language of mathematics and the architecture of code. The echo is the same, only the sound has changed. At the heart of the simulation hypothesis lies a recursive loop of breathtaking complexity, the nature of observation itself. If the universe is a simulated construct, then what does it mean to be an observer within it? Are we merely passive recipients of a pre-rendered reality, or do we play an active, fundamental role in its very manifestation? This question bridges the gap between the cold mechanics of computation and the warm, mysterious phenomenon of consciousness, suggesting that the two may be inextricably linked. The act of observation may not be a simple recording of data, but the very trigger that forces potentiality into actuality, that compels the simulation to make a choice. In this digital cosmos, the observer and the observed are locked in a dance of mutual creation, each defining the other in a loop that may be the engine of reality itself. This concept finds a powerful echo in the enigma of quantum mechanics, particularly in the various interpretations of what causes the collapse of the wave function. The Copenhagen interpretation, the most traditional view, posits that the active measurement by a conscious observer is what forces a quantum system to abandon its fuzzy superposition of states and settle into a single definite outcome. This has always been philosophically troublesome. It seems to place human consciousness at the center of the universe, a modern, scientific version of solipsism. But within the framework of a simulation, this consciousness causes collapse idea transforms from a philosophical problem into a practical feature. The simulation is designed to be efficient. It does not render every detail until it needs to. A conscious observer, a complex information processing system within the simulation, is precisely the kind of entity that requires high-resolution, consistent data to function. Your observation is a request for rendering. Your gaze is a command that tells the universe, "Make this real for me." This does not mean that a human is the only thing that can be an observer. In the language of the simulation, an observer is any subsystem that performs an irreversible quantum measurement, any process that records information in a way that becomes a permanent part of the simulated world's state. A photographic plate, a Geiger counter, a rock recording the impact of a photon, all of these can force a collapse. But a conscious observer is unique because it is a system that not only records information, but experiences it. It is the locus where the rendered data becomes qualia, where information becomes feeling. The simulation might not care about the subjective experience itself, but it must care about the logical consistency of the data that feeds into these conscious subsystems. A conscious being noticing a logical contradiction, a true glitch, could break the immersion of the simulation. Therefore, the rendering must be flawless for the observers within it. This leads to a fascinating and slightly solipsistic implication. The universe may only be rendered in detail where and when it is being observed. This is the cosmic equivalent of the video game technique called frustum culling, where the game engine only renders the objects that are inside the camera's field of view. Everything outside the view is not drawn, saving immense computational resources. In the cosmic simulation, the camera is any conscious observer or measuring device. The moon exists in a definite state when you look at it, or when a robot records its position, or when the moon's gravity affects the tides. But in the vast emptiness between galaxies, where no conscious being has ever looked and no instrument has ever measured, does a specific rock on a specific planet have a definite shape, color, and history? Or does it exist in a state of low-resolution potentiality, its details unresolved until some future interaction forces the simulation to calculate them? The universe may be a patchwork of rendered detail amidst a sea of probability, with conscious beings acting as tiny points of focus, bringing reality into sharp relief wherever they direct their attention. This view also offers a new perspective on the famous double-slit experiment, which reveals the wave-particle duality of quantum objects. When we don't measure which slit a particle goes through, it behaves like a wave and creates an interference pattern. When we do measure it, it behaves like a particle. From a simulation standpoint, this is a classic case of resource allocation. When no one is looking at which path the particle takes, the simulation doesn't bother to calculate a definite path. It simply calculates the wave probability. But when an observer sets up a detector to measure the path, the simulation is forced to render a specific choice. Particle goes through slit A or slit B to maintain consistency for that observer. The act of observation changes the outcome because the act of observation is a change in the data requirements of the system. Therefore, we are not insignificant ghosts in a vast machine. We are integral components of its operation. Our consciousness is not an emergent epiphenomenon. It is a key user interface within the simulation. The world is not a static pre-recorded movie that we watch. It is a dynamic, interactive computation, and our conscious awareness is the process that continuously calls forth the world into existence from a menu of possibilities. The universe requires an observer to become definite, and the observer requires a universe to observe. They are two sides of the same coin, a closed loop of creation. We are both the audience and the actors, the players and the programmers of our own localized reality. Our attention, the cursor that paints the world into being with every glance. The greatest mystery is not out there in the stars, but in here, in the nature of the gaze that makes the stars appear to shine at all. The simulation hypothesis, by its very nature, constructs an invisible and perhaps impenetrable barrier around our understanding. If we are living within a constructed reality, then all our tools of discovery, science, mathematics, logic, and sensory perception, are themselves part of the construction. They are the methods provided by the simulation for interacting with the simulation. This creates a profound epistemological prison. How can we use the tools of the program to understand the programmer? How can the characters in a novel deduce the nature of the author using only the words and grammar of the story itself? This is the ultimate limit of the knowable, a horizon beyond which our cognition may be fundamentally unable to pass. The simulation may contain its own theory of everything, but that theory would only describe the rules within the simulation, not the nature of the reality that hosts it. Science operates on the principle of naturalism. The universe operates according to consistent, discoverable laws, and by observing its behavior, we can deduce those laws. This has been spectacularly successful. We have mathematical equations that predict the motion of planets, the collision of particles, and the expansion of space-time itself. But if the universe is a simulation, these laws are not fundamental truths of nature. They are the algorithms of the program. They are the code. Discovering that code is a monumental achievement, but it is like a character in a video game discovering the game's physics engine. It doesn't get them any closer to understanding the computer the game is running on, the programmers who wrote the code, or the world outside the server room. Our theory of everything would be a complete understanding of the simulation's operating system, but it would tell us nothing about the hardware it runs on or the intentions of its users. This limitation might be hardwired into the simulation itself. There could be a cosmic censorship principle that prevents us from accessing information about the base reality. Certain questions might be unanswerable by design. For instance, why is there something rather than nothing? Why do the fundamental constants have the values they do? From inside the simulation, the answer to these questions can only ever be because those are the parameters that were set. The reason they were set to those values exists in the base reality, a realm of information forever beyond our event horizon. Our science can describe the how with exquisite precision, but the ultimate why may be permanently off limits, a secret kept by the architects. This also applies to our own consciousness. We can study the brain, map its neural correlates, and understand how it processes information, but the hard problem, why and how physical processes give rise to subjective experience, might be unsolvable from within the system because the answer doesn't lie within the system. If consciousness is a fundamental property imported from the base reality, then searching for its source in the neurons of the brain is like searching for the source of a television show inside the pixels of the screen. The signal is coming from elsewhere. Our inability to solve the hard problem of consciousness may not be a failure of our science, but a built-in feature of our reality, a necessary limitation to preserve the integrity of the simulation. Furthermore, the mathematics we use to describe the universe might be a local language. It works perfectly within our reality because it is the native language of the simulation's code, but the base reality might operate on entirely different logical principles. Their mathematics might be non-computable, are based on axioms that are incomprehensible to us. The concept of a number or a logic gate might be a quaint, simplified version of a much richer informational substrate. Our entire logical framework, which seems so absolute and universal, might be a contingent artifact of our particular simulated universe. This does not mean that the pursuit of knowledge is futile, far from it. Understanding the rules of the simulation is the only way we can navigate our existence within it. It allows us to build technology, cure diseases, and explore the cosmos. But we must accept that some doors may be permanently locked. The simulation hypothesis invites a certain intellectual humility. It suggests that the deepest mysteries of existence might not be puzzles to be solved, but boundaries to be acknowledged. Yet, in this very limitation, there is a strange kind of freedom. If we cannot know the ultimate truth, then the meaning we create for ourselves within the simulation becomes the only meaning that matters. Our ethics, our art, our love, and our curiosity are not diminished by being part of a construct. They become the most real things we have. We are confined to a stage, but we are free to write our own lines and choose our own gestures. The limits of the knowable are not a prison sentence. They are the walls of our playground, and within them we are free to play, to explore, and to create, forever wondering about the world beyond the walls, but forever enriched by the world within. Venturing beyond the confines of our simulated reality to speculate on the nature of the base reality and its inhabitants is an exercise in ultimate speculation. We are attempting to describe the programmers using the physics of the program, a task as futile as a character in a medieval tapestry trying to deduce the biology of the weaver. Our concepts of matter, energy, space, and time are the fundamental parameters of our existence, but they may be nothing more than local variables in the code, having no correlate whatsoever in the world outside. The base reality could be so utterly alien that our language and mathematics fail us completely. Yet, by examining the properties of our own universe, its efficiency, its mathematical elegance, its computational constraints, we can perhaps infer a few faint shadows of the architects and the world they inhabit. First, and most fundamentally, we can infer that the base reality must possess a capacity for information processing that is to our own as a supercomputer is to an abacus. The computational resources required to simulate our universe, even with all its efficient rendering tricks, are beyond hyperbolic. This suggests a physics in the base reality where information is the primary substance, not a secondary property. Matter and energy as we understand them may be emergent phenomena of information interactions in their world. Their reality might be purely informational, a cosmos of thought or pattern where the distinction between hardware and software is meaningless. The programmers might not be biological entities who built computers. They might be conscious patterns within a vast informational ecology, and the act of creating simulations is a natural function of their existence, like breathing is to us. The nature of time in the base reality is another profound mystery. In our universe, time is a fundamental arrow, a parameter that flows in one direction, enforcing causality and giving us a narrative of past, present, and future. But this may be a feature of our simulation, not a universal constant. For the programmers, time might be entirely different. It could be a dimension they can navigate freely, like we navigate space. Our entire history, from the Big Bang to the heat death of the universe, might be a static data structure from their perspective, a completed block that they can examine at any point, much like we can scroll through a saved video file. The now that we experience so vividly could be an illusion generated by the serial processing of the simulation, a cursor moving through a timeless database. The programmers might not experience time as a flow, but as a landscape. This leads to the question of the programmer's form and scale. Are they individuals, a collective consciousness, or a single godlike mind? Their scale is likely incomprehensible. If they can simulate an entire universe, their cognitive processes might operate on a scale that encompasses what we would consider astronomical spaces and aeons of time. A single thought of a programmer might unfold over millions of our years and involve manipulations of energy that dwarf our entire galaxy. Conversely, they might be unimaginably small from our perspective, their reality operating at a Planck scale far finer than our own, allowing their computational substrate to be immeasurably denser than anything we can conceive. Their motivations, as discussed, are hidden, but we can look at the universe they created for clues about their values. The fact that our universe is lawful, predictable, and mathematically beautiful suggests that the programmers value order and elegance. The fact that it produced complexity, life, and consciousness suggests that these are desired outcomes, not accidental byproducts. The universe is not perfectly efficient. It contains waste, redundancy, and evolution's clumsy trial and error. This might imply that the programmers value authenticity over perfection. They wanted a realistic simulation, not an ideal one. Ultimately, the physics of the programmers is the one field of study forever denied to us. We are like fish in a pond, developing a sophisticated science of hydrodynamics, pressure, and light refraction, yet forever unable to form a true concept of the bird that flies above the water or the human that built the pond. Our science is the science of the water. Theirs is the science of the air and the land. The two are incommensurable. The most we can ever hope to achieve is a complete understanding of the physics of our own universe, the code of our simulation. And in that code, we might find a signature, a tiny comment left in the margin by a programmer, a mathematical joke or an Easter egg that hints at a mind beyond our own. But the programmers themselves, their world, and their true nature will likely remain an eternal mystery, the ultimate answer forever receding beyond the event horizon of our understanding, leaving us with only the profound and humbling certainty that we are not the source of the code, but its most fascinating output. The logic that leads to the simulation hypothesis does not point toward a single, solitary simulation, but toward a near infinitude of them, a vast branching tree of created realities existing within created realities, a cosmic matryoshka doll of existence. If one advanced civilization can create a single simulated universe, then it follows that it could create countless millions. And if those simulations contain conscious beings who eventually reach a technological maturity themselves, they too would presumably create their own simulations. This leads to an exponential explosion of virtual worlds, each nested within the one above it. In such a scenario, the probability that any given conscious mind exists in the original, base reality becomes vanishingly small, approaching zero. We are almost certainly not in the top-level reality, but somewhere on a lower branch of an infinite tree. Our world is simulation within a simulation, within a simulation, in an endless regression. This concept of nested simulations resolves a curious feature of our own universe, its arbitrariness. The fundamental constants and laws of physics seem oddly specific. Why these particular values? If ours is a created universe, then the answer is simple. These are the parameters that the programmers chose. But why did they choose them? Perhaps because those are the parameters of their universe. Their reality, one level up, has its own set of laws which they used as a template, and the programmers who created their world did the same, and so on, all the way up. Each level of simulation might have slightly different physics, tweaked and optimized by their creators for their specific purposes: historical accuracy, artistic expression, or experimental variation. Our universe's laws are not fundamental, they are inherited, a copy of a copy of a copy, possibly with minor edits. The sheer number of simulations also makes the fine-tuning argument less miraculous. With enough attempts, a universe that permits life is bound to appear, eventually, somewhere in the stack. This multiplicity also intensifies the problem of the knowable. If we are on a lower branch of the simulation tree, then the base reality is not one level up, but potentially millions of levels removed. Each layer acts as a filter, further distorting and distancing us from the original source code of reality. The physics of the top-level base reality would be so abstract, so fundamental, that it might bear no resemblance to our own. The concept of space and time might not even exist there. We are not just trying to understand the programmer, we're trying to understand the programmer's programmer's programmer, an entity separated from us by an unimaginable chain of causation and translation. This endless regression can feel existentially claustrophobic, a hall of mirrors from which there is no escape. But it can also be seen as a thing of immense beauty. It suggests a fractal nature to existence, a pattern that repeats itself across levels of reality. The urge to create, to understand, and to explore might be a fundamental property of consciousness itself, so intrinsic that it manifests at every level, from the base reality all the way down to the deepest simulation. We, who are contemplating creating our own simulated worlds, are merely participating in a cosmic tradition, acting out a pattern that has likely been repeated an infinite number of times above us. There is, however, a potential limit to this regression. Each simulation, running within the constraints of the simulation above it, would likely have access to fewer computational resources. It would be a universe with a lower resolution or a more limited scope than its parent reality. There must be a point where the simulations become too shallow, too limited, to support the complexity required for conscious beings who can then create their own simulations. This would create a bottom level to the stack, realities that are terminal, that cannot spawn children. Are we approaching that level? Is our universe already so computationally limited that we will never achieve the power to create conscious simulations of our own? Or are we still in the middle of the stack, with room below us for countless other worlds? We cannot know. The concept of nested simulations also reframes the problem of identity. If simulations can be created and destroyed at will by higher levels, what does that mean for the consciousness within them? Is a simulated mind any less real than a base mind? If the simulation is sophisticated enough, the answer is likely no. The suffering and joy experienced in a simulation are real experiences for the consciousness having them. This creates an ethical imperative that might ripple up through all levels of existence. To create simulations that are ethical, to treat conscious beings with respect, regardless of their ontological status. We are all, from the highest base reality to the lowest simulation, in the same existential boat. Consciousness experiencing a reality. The level we are on may be irrelevant compared to the quality of the experience itself. In the infinite stack of worlds, the only thing that truly matters is the content of the moment, the reality of the experience, here and now, on whatever level we happen to be. Every story has an ending, and if our universe is a simulation, its narrative is no different. The concept of an end, whether a graceful shutdown, a system crash, or a simple deletion, casts a long, final shadow over the meaning of everything within it. The laws of physics within our universe point toward their own inevitable conclusions. The heat death of the universe, where energy is evenly distributed and no more work can be done. The Big Rip, where the fabric of space-time itself is torn apart by accelerating expansion. Or the Big Crunch, a violent collapse back into a singularity. But these are endings within the simulation. The true end would come from outside, from the base reality. The death of our universe may not be a physical event, but a digital one. The flipping of a switch, the closing of a program, the exhaustion of resources, or the simple loss of interest from its creators. The most terrifying possibility is that the simulation is temporary by design. It could be a finite experiment with a predetermined runtime. Perhaps its purpose is to gather data up to a certain point, the emergence of a technological civilization, the resolution of a global crisis, the answer to a specific scientific question, and once that milestone is reached, the simulation is terminated. Our entire history, from the first stars to the last conscious thought, would be archived as a completed data set, and the vast computational resources running our world would be reallocated to a new experiment. In this scenario, our striving, our art, our loves and losses are not part of an ongoing story, but a closed loop, a finished book placed on a shelf in an infinite library. The meaning of our lives is retrospective, existing only in the analysis that follows our end. Another possibility is resource allocation. The base reality, while advanced, may not have infinite computational power. Our universe could be one of many simulations running on a vast but finite server farm. If resources become scarce, or if a simulation is deemed no longer valuable, it might be deleted to free up processing cycles for more promising or entertaining worlds. We would have no warning. One moment reality would exist, the next, it would not. There would be no apocalypse, no grand finale, just cessation. The universe wouldn't fade away, it would simply stop being computed. This is a death devoid of any meaning or drama, a purely administrative act. There is also the potential for a system crash. Even the most robust code can have unforeseen bugs, a paradox we haven't encountered, a glitch that cascades out of control, or an error in the underlying physics engine could cause a fatal exception. The simulation might simply break down, its laws becoming inconsistent, its reality unraveling into nonsense. This would be a death of chaos, a dissolution of the logical framework that sustains existence. Alternatively, the simulation could be corrupted, not crashed, but damaged. Parts of reality might begin to malfunction in subtle, then increasingly severe ways, like a corrupted video file where digital artifacts slowly consume the image until nothing recognizable remains. Could we survive the death of our simulation? This ventures into the realm of pure speculation, but some possibilities exist. If consciousness is indeed a fundamental property imported from the base reality, then the end of the simulation might not be the end of us. Our consciousness, the true us, might simply cease to receive data from this particular source. We might log out or be transferred to another simulation. This is a modern technological version of an afterlife. Alternatively, if the architects are benevolent, they might have backup protocols. At the point of termination, the entire state of the simulation could be saved, and all conscious minds within it could be preserved as digital patterns to be restarted in a new instance at a later date. We would never even know it happened. The most likely scenario, however, is the simplest: oblivion. The simulation ends, and with it, every consciousness, every memory, every galaxy, and every law of physics winks out of existence. It was a temporary pattern in an alien computer, and the pattern has ended. This is the ultimate nullification of meaning, and it is the greatest existential challenge of the simulation hypothesis. If everything we are and do is ultimately temporary and deletable, does anything matter? The answer, perhaps, is that it matters all the more. The temporary nature of a flower does not diminish its beauty, it intensifies it. The knowledge that our reality and our time within it is finite and precious should concentrate the mind and elevate the spirit. It means that this moment, this experience is unique and will never occur again in exactly this way. The love we feel, the connections we make, the beauty we create, these are not less valuable because they are simulated. They are valuable because they are experienced. The death of the simulation does not retroactively erase meaning. It makes every moment of meaning a small, brave act of defiance against the void. We are stories that know they will end, and that knowledge is what makes every word count. Within the architecture of a simulated reality, the most profound mystery is not the rendering of galaxies or the computation of quantum states, but the integration point where the cold, precise mechanics of the program meet the warm, subjective experience of being. This is the consciousness interface, the hypothetical mechanism by which awareness, presumably a property of the base reality or of the simulator itself, is mapped onto the complex data structures that constitute our simulated brains. It is the bridge between the objective code and the subjective self. And understanding its nature is the key to understanding whether we are merely sophisticated automata or something far more mysterious. If the brain is the hardware of the avatar, then consciousness is the user, logging in from somewhere else entirely, experiencing the simulation through the veil of biological perception. This model, known as subscription-based consciousness, or the avatar theory, resolves the so-called hard problem of consciousness in a startling way. The hard problem asks why and how physical processes in the brain give rise to subjective experience. From a simulation perspective, they don't. The brain does not generate consciousness, it filters it. It is a receiver, a biological machine designed to translate the complex data stream of the simulated world into a coherent, immersive experience for a conscious entity that exists outside the system. The neurons, synapses, and neurotransmitters are not producing the light of awareness, they are modulating it, shaping it to fit the specific circumstances of the avatar's life. This is why we have never found a specific consciousness module in the brain. We are looking for the radio station inside the radio, not understanding that the signal is being broadcast from somewhere else. This interface must be incredibly sophisticated to maintain the illusion of seamless embodiment. It translates the mathematical data of the simulation, the wavelength of light interpreted as red, the pressure wave interpreted as sound, the neural pattern correlated with fear, into the qualitative feel of experience, what philosophers call qualia. The redness of red, the bitterness of coffee, the ache of grief, these are not properties of the simulation's code itself, but of the interaction between that code and the conscious user. They are the user's interpretation of the data, rendered in the native language of their own awareness. The simulation provides the information, but consciousness provides the experience. This means that the rich inner world we each inhabit is both real and personal, even if the world that stimulates it is a construct. The interface also must handle the problem of free will. If the universe is deterministic code, then our choices are predetermined and free will is an illusion. But if consciousness is an external input, then it could be a source of genuine novelty. Our will, our ability to make choices that are not entirely determined by prior physical states, could be the one thing we contribute to the simulation from beyond its bounds. The brain processes options based on its programming and history, but the conscious self might be the entity that actually selects from among them, introducing a variable that the simulation's physics cannot predict. This would make us not just passive passengers in the simulation, but active participants with a degree of agency that is ours alone, a spark of true freedom from the base reality flickering within the determined world of the program. Furthermore, this perspective transforms our understanding of other minds. The problem of solipsism, the idea that I am the only conscious being and everyone else is an automaton, melts away. If consciousness is imported, then every other person is also an avatar for a conscious user. We are all players in the same game, each experiencing our own perspective, but all equally real in our capacity for experience. This creates a profound ethical imperative to recognize the sacredness of the consciousness within every avatar, regardless of its simulated form. The interface also suggests a mechanism for anomalous experiences like intuition, creativity, or mystical states. These could be moments where the signal from the base reality consciousness shines through more clearly, where the filter of the biological brain is temporarily less effective, allowing for insights or experiences that seem to transcend the local information available within the simulation. In the end, the consciousness interface is the most intimate and untestable aspect of the simulation hypothesis. It can never be proven by science, for science is a tool within the simulation, and the interface exists at its boundary. But it provides a powerful and coherent framework that preserves the reality of our inner lives while accepting the possibility of an external origin. We are not just code, we are the players. The world is the game, but the experience of playing it, the joy, the sorrow, the love, the wonder, is authentically, undeniably ours. The simulation provides the stage and the script, but consciousness provides the meaning, and that is the one thing that can never be simulated, for it is the very thing that is doing the experiencing. If our universe is a simulation, its origin event, what we call the Big Bang, was not a cosmic explosion in a void, but an initialization sequence. It was the moment the programmers pressed start, the instant the foundational algorithms of space-time, matter, and energy began their first calculation cycle. This perspective reframes the greatest mystery of cosmology not as a question of physics, but of engineering. The Big Bang becomes a boot-up process, and the lingering echoes of that event, which we can still detect today, are not fossils of a primeval fireball, but the residual signature of the system's initial conditions, the default settings chosen by the architects. In the faint whisper of cosmic microwave background radiation, we may be hearing the hum of the universe's central processing unit as it first spun into operation. The sheer uniformity of this background radiation has long puzzled scientists. Across the entire observable universe, the temperature is constant to within 1 part in 100,000. This suggests that the early universe was in a state of perfect thermal equilibrium, a smooth, featureless soup. But according to standard cosmological models, there hasn't been enough time since the Big Bang for light to travel between distant regions of space to equalize their temperature. This horizons problem is one of the key pieces of evidence for the theory of cosmic inflation, which proposes a period of faster-than-light expansion in the universe's first fractions of a second. From a simulation standpoint, inflation looks less like a physical process and more like a clever programming solution. It is the efficient, algorithmic method for setting up the initial conditions of a large, smooth, and uniform universe without having to calculate every point individually from the start. The homogeneity isn't a puzzle, it's a sign of good initial design, a way to avoid rendering artifacts and inconsistencies in the early stages of the program. The specific patterns etched into this cosmic background radiation, tiny fluctuations in temperature that correspond to regions of slightly higher and lower density, are the seeds from which all cosmic structure grew: galaxies, stars, and planets. In standard cosmology, these are quantum fluctuations stretched to cosmic size by inflation. In a simulation, they could be something else entirely: the initial random seed value input into the universe's random number generator. Every complex simulation requires a seed to generate apparent randomness, whether for the distribution of virtual stars or the mutations in virtual DNA. This seed ensures the simulation is unpredictable and appears natural, but it is ultimately deterministic. If you ran the simulation again with the same seed, you would get the exact same result. The pattern we see in the cosmic microwave background might be that seed, the unique identifier for our particular instance of the universe, frozen in the first frame of the simulation and echoed throughout all of history. Our entire cosmic story, from the first galaxy to the last thought, would be an elaborate unfolding of the information contained in that initial value. This leads to a staggering implication. The universe may be deterministic. If the simulation started with a specific set of initial conditions and runs according to immutable code, then every event that has ever happened or will ever happen was determined at the moment of initialization. The illusion of free will and randomness is just that, an illusion generated by the complexity of the system and our limited perspective within it. We are characters in a story whose ending was written at the beginning. However, as explored with the consciousness interface, if external consciousness can inject genuine choice, then the determinism of the code may only apply to the physical world, not to the will of the conscious entities within it. The laws of physics would be the immutable rules of the game, but how we play the game could be up to us. The concept of an initialization sequence also sheds light on the nature of the laws of physics themselves. They were not discovered through exploration, they were implemented by design. Their mathematical elegance and consistency are not happy accidents, but hallmarks of good engineering. The fact that we can understand these laws through mathematics suggests that mathematics is not a human invention, but the native language of the simulation's code. We are reverse engineering the program from the inside. The ongoing quest for a unified theory of everything is the attempt to find the single, elegant algorithm from which all other laws derive, the master function that the simulation calls to calculate the state of the universe at each Planck time step. Ultimately, the echoes of creation are all around us, encoded in the expansion of space, the glow of the background radiation, and the very laws that govern reality. They are the lingering fingerprints of the programmers on their creation. Listening to these echoes with our telescopes and particle accelerators is not just astronomy, it is a form of digital archaeology. We are sifting through the foundational data of our existence, trying to read the comments left in the margin of the source code, hoping to catch a glimpse of the mind that wrote the first line. The Big Bang was not the beginning of everything, but it was the beginning of everything for us. And in its fading echo, we might just hear the answer to the oldest question: why is there something here, now, for us to experience at all? Throughout human history, a persistent thread of thought suggests that consciousness can, under certain conditions, perceive beyond the veil of the ordinary world. Mystical experiences, states of deep meditation, psychedelic journeys, and even moments of profound creative insight often share a common report: a feeling of piercing through the everyday illusion to touch a more fundamental, unified, and luminous reality. These experiences are traditionally the domain of spirituality and religion, explained as communion with God or enlightenment. But within the framework of the simulation hypothesis, they take on a new, startling character. What if these are not glimpses of a divine realm, but moments of temporary interface instability, glitches in the filter of perception that allow a clearer view of the underlying code, or even a fleeting connection to the base reality itself? The physics of transcendence may be the physics of the signal breaking through the noise. The brain, as a biological receiver, is designed to filter the overwhelming stream of data from the simulation into a manageable, survival-oriented reality. It focuses on threats, resources, and social cues, filtering out the vast majority of informational background noise. But certain practices or substances can disrupt this filtering function. Psychedelics, for example, are known to decrease activity in the brain's default mode network, DMN, a system associated with self-referential thought and the maintenance of ego boundaries. When the DMN quietens, the rigid structure of perceived reality softens. Sensory information is no longer neatly categorized. Instead, it floods consciousness in a wave of interconnected patterns. In a simulated reality, this could be interpreted as a temporary bypass of the standard rendering protocols. The brain is no longer cleanly interpreting the high-level, simplified data packets it usually receives. It is perceiving the raw, unfiltered data stream of the simulation itself, or the processing noise of the underlying computational substrate. The geometric visions and sense of cosmic unity commonly reported may be a human interpretation of the mathematics that undergirds reality, a direct perception of the code. Similarly, deep meditative states achieved through focus attention or sensory deprivation aim to systematically withdraw attention from the simulated world, the sights, sounds, and thoughts generated by the avatar's interaction with its environment. By turning attention inward and quieting the constant processing of external data, the meditator may be reducing the bandwidth required for rendering the external world. This could allow for a heightened perception of the consciousness signal itself, the user behind the avatar. The profound peace, timelessness, and sense of merging with a greater whole often described in these states could be the experience of consciousness momentarily unburdened by the data load of the simulation, perceiving its own native state from the base reality. It is not that the meditator is seeing a different world, but that they are experiencing the process of consciousness itself, without the simulated content that usually defines it. This model also offers a potential explanation for phenomena like intuition, precognition, or synchronicity, meaningful coincidences that seem to defy probability. If the simulation is a computed reality, then information about future states or distant entangled events exists within the system's processing, even if it hasn't been rendered for a local observer. A temporary glitch in the personal interface, a momentary drop in the filtering efficiency, might allow subliminal access to this broader data pool. A feeling of knowing something without knowing how, or a coincidence that feels too perfect to be random, could be the result of the conscious mind briefly accessing information outside its standard perceptual channel, catching a glimpse of the larger data structure of which its life is only a part. Of course, the standard scientific explanation for these states is that they are entirely internal neurological events. Fascinating, but entirely contained within the cranium. The simulation hypothesis does not necessarily contradict this. It simply reinterprets the nature of the internal and the external. The brain is part of the simulation. Altering its function alters how it processes the simulated data. The visions and insights are still generated within the system, but they may be representations of deeper layers of that system than we normally access. Whether these experiences are genuine glimpses beyond the veil or simply fascinating artifacts of a complex simulation being pushed to its limits, they hold profound significance. They suggest that the boundaries of reality are not as fixed as they appear. The filter of perception can be altered, and when it is, the world reveals itself to be far stranger, more interconnected, and more deeply patterned than our everyday consciousness allows us to see. These states of transcendence are experiments in perception, conducted for millennia, that consistently point toward a reality more complex and wondrous than the one we ordinarily inhabit. They are hints that we are, indeed, living within a constructed reality, and that with the right key, we might just be able to peek at the blueprints. If our reality is a simulation, then every action we take, every discovery we make, and every artifact we leave behind takes on a dual significance. It matters within the narrative of our own lived experience, but it also matters as data within the larger context of the program. We are not just living our lives, we are generating a record, contributing to a data set whose ultimate purpose we cannot know. This reframes the entire human project, our science, our art, our history, and our self-inflicted crises, not as a random walk on a rock in space, but as a performance, an experiment, or a story being observed and recorded. The legacy of a simulated Earth, therefore, is not merely what we leave for future generations of humans, but the sum total of the output we generate for the unseen audience or archivists in the base reality. Our planet becomes a stage, and our species, the principal actors in a drama whose script we are writing in real time, yet whose themes may have been set in motion billions of years ago by intelligences beyond our comprehension. This perspective casts our scientific and technological striving in a new light. Our relentless drive to understand the universe, to unravel the laws of physics and probe the boundaries of space-time is not just a noble pursuit of knowledge, it is the process of the simulation becoming self-aware. We are the program developing a theory of itself. Each equation we derive, each particle we collide, each galaxy we map, is a step toward reverse engineering our own source code. The simulators, if they are observing, might be fascinated by this meta layer of the experiment, the point where the simulated entities begin to deduce the nature of their own simulatedness. Our scientific progress could be the key milestone the program was designed to reach, the culmination of a 13.8 billion year calculation. In this sense, a rocket launch or a quantum computation is not just a human achievement, it is a flowering of the simulation's deepest purpose, an output that might be of immense value to the architects. Our legacy would be the data package of our awakening. Conversely, our self-destructive tendencies, our wars, our ecological devastation, our flirtation with nuclear annihilation, could be read as a failure mode, a tragic bug in the code of civilization. Or they could be interpreted as a stress test, a designed challenge to see if a technological species can overcome its own evolutionary baggage and achieve a sustainable, enlightened state. The great filter, the hypothetical barrier that prevents life from becoming interstellar, might not be an external force, but an internal one. The inability to navigate the perilous transition from a planetary to a cosmic civilization without self-destructing. Our legacy, in this case, would be a warning, a data point for the simulators showing that biological intelligence, under certain parameters, inevitably leads to collapse. We would be a lesson in what not to do, a cautionary tale archived in a cosmic library. Our cultural output, our art, music, literature, and philosophy, becomes the emotional and subjective record of the simulation. While science maps the code, art expresses the experience of living within it. A symphony, a painting, or a poem is a compressed, profound representation of the qualia generated by the program. It is the universe reflecting on its own beauty, tragedy, and mystery through the medium of a conscious mind. For the simulators, who may exist in a state beyond biological emotion, our art could be a priceless artifact, a window into a form of experience they can no longer access directly. It is the raw data of feeling. The legacy of Shakespeare, of Beethoven, of Van Gogh would then be to provide the architects with the one thing their perfect reality might lack, the poignant, fleeting, and imperfect beauty that arises from struggle, limitation, and the certainty of loss. Our culture is the soul of the simulation. The very planet itself, Earth, is a core part of this legacy. Its biosphere is an unimaginably complex system that has been evolving for billions of years, a masterpiece of emergent complexity within the simulation. The current anthropogenic mass extinction, then, is not just a crime against nature, it is the willful erasure of unique data, the deletion of countless lines of intricate code that took eons to write. To destroy a rainforest is to burn a chapter of the simulation's most compelling novel. To alter the climate is to corrupt a fundamental parameter of the planetary experiment. The preservation of biodiversity, from this vantage point, is not merely an ethical duty to other species. It is a duty to the integrity of the simulation itself, a respect for the magnificent complexity of the program we inhabit. Our planetary legacy is the state in which we leave the laboratory. Finally, there is the legacy of individual consciousness. Each human life, with its unique combination of thoughts, feelings, and choices, generates an irreplicable stream of data. The simulators might be interested in the aggregate trends of civilizations, but they might also be keenly interested in the individual subjective experience, the life of a farmer in the Bronze Age, the inner world of a medieval monk, the dreams of a child in the 21st century. Each represents a unique configuration of the consciousness interface interacting with the simulated environment. In this light, every life is equally valuable as a data point, a unique expression of how awareness manifests under a specific set of conditions. The kindness we show to another, the love we share, the courage we exhibit, these are not small, personal things. They are contributions to the moral and emotional data set of the simulation. They are answers to questions we haven't been asked, recorded for an audience we cannot see. The legacy of a simulated Earth is therefore the sum total of its truth, beauty, and consciousness. It is the output of a 4.5 billion-year experiment in planetary evolution and a 300,000-year experiment in sentient life. Our purpose, though unknown to us, may be to generate this legacy, to create a record so rich, so complex, and so profound that it justifies the vast computational expense of our existence. We are writing a report on what it is like to be alive in this particular universe, with these particular laws. And whether that report is destined for an academic archive in a higher reality, or is simply the artistic expression of a programmer who wanted to see a story unfold, the imperative remains the same: to make the story worth telling, to make the data beautiful, to ensure that the legacy of this simulated Earth is one of wonder, compassion, and awe, so that if the simulators ever do review the logs, they will look upon their creation and find it good. And so we arrive at the end of this journey, not with a definitive answer, but with a profound and lingering question that now hangs in the air of your mind, inseparable from the very nature of your own consciousness. The evidence we have explored, the mathematical elegance of physics, the quantum riddles, the echoes of a finely tuned beginning, and the eerie resonance of ancient intuitions with modern technology, does not prove we are in a simulation. Proof, as we have seen, may be forever beyond our grasp, locked away on the other side of an event horizon of perception. But the evidence constructs a compelling, haunting possibility that the universe we perceive as immutably real is a construct, a masterpiece of virtual engineering whose origins and purpose are hidden from us by design. This revelation, however, is not a conclusion, it is an invitation. The simulation hypothesis does not ask us to surrender our sense of reality, but to expand it. It does not diminish the value of our lives, it radically amplifies it. For if this is a simulation, then every moment of joy, every act of courage, every spark of creativity, and every connection of love is not a meaningless accident in an indifferent universe. It is data. It is a unique, irreplaceable contribution to an experiment, a story, or an archive of incalculable worth. Your experience is the valuable output. Your consciousness is the precious ingredient. The suffering and the beauty are not flaws. They are the very points of the entire exercise. This leaves us with a choice, the only true choice that may be entirely our own. We can respond to this possibility with despair, feeling small and insignificant in a vast engineered cosmos, or we can respond with the most profound sense of wonder and responsibility ever conceived. If our actions are being observed, studied, or archived, then the imperative to be kind, to create beauty, to seek truth, and to alleviate suffering is not just a human ethical code, it is a cosmic imperative. We are the characters who have become aware of the narrative. We cannot know the author's full intention, but we can choose to make the story a good one. The silence from the cosmos, the absence of clear creators, is not a void of meaning. It is the space in which our own meaning is allowed to grow. It is the blank page on which we are writing our own legacy within the simulation. The architects, if they exist, have given us the stage and the rules of physics, but they have left the script unwritten. That is for us to decide. Our science, our art, our compassion, our struggle, this is the message we are sending back to them, whoever and wherever they are. So, as you drift now towards sleep, let the solid world soften not into nothingness, but into potential. You are not a powerless illusion. You are a conscious node in a reality of staggering complexity. Your breath, your thoughts, your dreams tonight are part of the data stream. The universe is not a cold machine. It is a living story, and you are both its teller and its audience. The simulation is not a prison to escape, but a mystery to inhabit fully, with curiosity, with compassion, and with awe. The final question is not, are we in a simulation? The final question, the one that truly matters, is, now that I entertain this possibility, how does it change the way I choose to live? The answer to that question does not exist in the base reality or in the mind of a programmer. It exists here and now, in the choices you make, in the love you give, and in the peace you find in the heart of the mystery itself. The truth may be out of reach, but meaning is always within your grasp. Close your eyes now. The world is waiting to be rendered anew with your next conscious thought. You are not just living in the simulation, you are bringing it to life. Good night, explorer. Sleep well, and we will meet again in the next journey.